Hello, everybody. This is the databases and data lake intro. It's the one I've been reading because it can go so long, but hopefully we can keep it around about the 10 minutes. Um, so basically, everything you do um, in industry is going to have a database to hold the data. There's very many types of databases. Relational databases started off as the first, with IBM and Oracle having the famous ones. That would cost you millions of pounds of licensing, but certainly there's now plenty of free ones like MySQL, Maria, Postgres, and the cloud vendors also give you managed service of these, so it saves the staffing. Um, as a rule of thumb, if you're doing a teeny database, it can sit within an application. You probably do SQLite. Um, a slightly bigger app or a medium-sized app, you would probably want to use MySQL or Maria. And if it's larger, start with Postgres. Postgres can scale immensely. It's a really good option. But as you can see, there's lots of different types of databases. So what we're going to do is cover them. Relational databases are used for the online transaction processing at the beginning of most websites. And then the, the machine learning and the data analysis is done in a data lake, which tends not to be doing live data, or if it is, it's getting streamed in, just topped up on the database. So the high performance, high workload databases, we tend to have at the front, and then the ones we do the machine learning and the analytics and all the AI tend to be not getting hit so fast. Their data tends to be used for machine learning. So we'll have a wee look at the different types of databases. Um, as you can see, AWS, Azure, and GCP all have a multitude of databases as well. Same first principles for some. You can probably see there's Postgres and MySQL available as managed service, which means they take care of the backups, the failovers, all that sort of stuff. But there are still many different types of databases, so you have to at least know roughly what you're looking for to start with. You can change with time, but there's plenty of options. So what is a relational database? A relational database basically has lots of different tables. They just look like Excel spreadsheets. So they've got maybe a patient ID, name, birth date, address, email. And what makes it relational is that you can have one element linking to another table. So like in this case, we've got the patient ID is used by the other tables as well. And if you look at it, it makes it simple. It's like, or if it's an ordering database, you would have someone's address in one table, and any time they ordered something from you, you would just look it up and stick it on the envelope and post it off. And you probably give the same address to the bank when you try to use your payment card. So it's all good. Um, as I say, SQLite, if your database is in an app, it's actually in the Airbus A350 and it's guaranteed 40 years more support, so tiny ones. But I would probably MySQL and MariaDB, they're both the same thing essentially, different licensing, but they're both free. Postgres for a big database is where I would start these days. Obviously, Oracle, IBM, and Microsoft have been there in the past, but they're expensive. Microsoft have got nice new serverless SQL databases and that save you a fortune, but that's not for an intro course. That's for deep diving. So now in the world of cloud and big data. So what we have is we've got a primary database, and when it crashes, we lose everything. So people have come up with secondary databases, and now we've got read replicate databases. So any data is written to the primary, and it's synced out to all the other databases. Um, RDS tends to have something called ACID, which means it's guaranteed. It means you don't get corruption. It's basically a shared connection. So a write happens in the primary, and then it's sent out to all the read replicas before they let anyone else read from them. So it's really good. It's the way we do things now. When you get to industry, migrations and upgrades, one of the main concerns about your implementation will be ensuring there's no loss of data. and we focus on this. There are full-time jobs called DBAs, or database administrators. This is a full-time job, just looking after relational databases, whereas a data engineer looks after the other kinds of databases, but obviously understands the SQL to do it. So as you can see, we've got, in this scenario, we've got four database servers and either one logical database sent across them all, or we've got three different databases. So if you're using cloud, I would use the top one and just scale your databases for your logical database and separate it. And this means that any work you can be doing, you're only going to affect your medical logical database. Whereas the example before, at the below, if you've got multiple big servers, there's no point, physically in a room. You may as well put all your databases across them all and get the availability of having four machines. But you just have to take in consideration when you're upgrading, you're going to be affecting more logical databases. But it's how to get value for money and sweat the assets. So hopefully that makes sense. So most people, if they just say the word database, they're talking about relational database. So that's what we've covered here. NoSQL databases, they're much simpler. They're really good. You would use them if you're writing. Sometimes they're referred to as document databases. So we've got a key and we've got a JSON string essentially. Normally you're going to have something consistent, like you're going to have people cards for people and maybe address cards for addresses, but you're not really constrained. You will, and when we do this, when we experiment in some examples in future episodes, we will have the JSON consistent, and it will make a lot of sense. But had you been doing things for years and then all of a sudden you need to add an extra parameter, like you need a mobile phone, in a relational database, that can be a nightmare to add, whereas you just add it as a new thing in the schema and it's all good for the JSON. So NoSQL databases are brilliant. The example in the bottom is based on HBase or Google Cloud Bigtable, and the file system is HDFS, which comes from Hadoop, which was a early machine learning product. Google buckets or Google Cloud Storage buckets are HDFS compatible, so you can have the data just in Cloud buckets, and the nodes they're all same machines, and you just spin them up and they get a partition in the database and they serve the data and it scales. The more data you want to serve, you just need more and more nodes. It's very scalable, very powerful. You can get planet scale. They are quite often used for keeping scores in computer games, online multiplayer computer games, so that you can keep sessions all the same. We're going to come up against Redis, which is also used. It's a cache database. It's good for keeping scores too. And as the world is overlapping, more of these products are merging and they can do what each other can do. So to start with, like Mongo was the best one at just being a NoSQL database. Redis was the best at being cache. And Neo4j was the best at graph, but they're all overlapping and they're all doing the same thing because they all want to support LLMs and AI. So cache database, it's very simple. You put a key and a value and it's just paired. Redis changed its licensing, so valkey came out and it's the open source equivalent, and basically you just run it in a container and the file system's used for backup. Very simple, very fast. There are high availability patterns, but the database memory is cached between all these containers. So it's very, very fast. Everything's in memory, and if you turn it off, everything goes. So it's used for, as I say, scores in computer games and anything else. There are patterns that you can cache to make relational database faster by using a bit of Redis. But that's maybe a bit advanced for now. But cache databases, just think of them as really simple, really fast, and they're brilliant, and you don't save data long term. Graph databases, so they're basically graph things. So they work out relationships. So as we can see, if we put the man and the lady in the middle, they're probably married because they've got the same savings account. They work in different places. They own a phone each. There's somebody else that works for the builder, and he owns a cell phone. And then you can do the clever stuff. Like you could guess they're married because they've got the same savings account. And you can see there's been 20 calls between their mobile phones. So that's consistent. Whereas the lady and the man who works in the builders, there's been 10 calls between them. We can establish that. Can we work out if they're work calls or whether they've got friends or whether they've got a personal relationship? That's for the future, but that's what graph databases essentially do, is to let you work out stuff. And if you're an intelligence service or intelligence agency or something like that, it's a very good way to get lots of information about people you care about, because all of a sudden the data stacks up very quickly. So these 3 lines in red are implied. Time series database. Now, Influx was the leader, and it was the best. But now with Internet of Things, so IoT, lots of devices, and I've worked with companies where they've got lots of sensor flows and stuff like that. Prometheus is actually a time series database, but it's always paired with Grafana, which is the graphical user interface for the top. So all metrics in Kubernetes and many other systems go into Prometheus time series database with Grafana doing the graphs, whereas Influx is the traditional time series. And you could be recording speeds of a car, water pressure sensors, anything like that comes in series, like time based numbers, and that's what they're optimized for high performance, for giving you the data back. Vector databases, they're new. They come with large language models, and they started off by being the vehicle for allowing conversations to be retained between all of the LLMs. So if you ask three or four questions, they were used for that. But how they work under this scenes is words in an LLM, they're read and they're tokenized, and so rather than the words themselves, it's actually tokens. And this is a 2-dimensional graph, but in reality, there are hundreds of dimensions. And what they do is they use clever maths, and as luck would have it, similar words all grouped together and have a similar vector. So we've done, there's animals up to the top right here, and there's fruit down to the bottom left. So very different things, but that's how it works. They group things together, and that's how the LLMs can work if you're meaning the same word or similar words. So obviously that's a subject in its own. The maths are quite complicated, but because it's all to do with vectors. So if you think back to your school days and how you did vector sums and cosines and stuff like that, you can work out what words are closest together by how close their tokens are. Weaviate and Pinecone being 2 of the big ones. Elastic, as it's merged into everything else, but it used to be the best one for search. So if you used lots of search queries, like if you were doing an internal version of Google, typically it was to do with computer logs or stuff like that. Elastic was the product you used, but as I say, Redis and is catching up with it, and they're all merging, they're all doing the same thing. But Elastic was the first one to be a search database. And here we come to so I should have said, in relational databases, you can actually export your table as a CSV, or actually the whole database can be exported as a Parquet or Avro file. Data lake houses expect like a cloud bucket, like S3 or Google Cloud Storage, and we just put lots of the Parquet files or whatever output, and we just put it onto a big file system. Databricks is probably the most famous data lake house, and it's available on all 3 clouds, as you can see, and you can run it yourself. And basically you just throw all data into different cloud buckets, and then it gets wrapped with layers of data management and governance, platform security. So that's the authentication, where it runs, and it's all really good. And you can obviously, it's got machine learning packages and data science packages that go through the can perform functions on the data. And on the right hand side, you can see this is a view of maybe a data analyst or a data engineer. So the first bit of data comes in, it's called bronze normally, and that's the raw data, and that's cached there. Then they've got a silver layer, which is the refined layer, which they do maybe error check and make sure all the bad readings get taken out. If there's missing readings, maybe they try and fetch it from somewhere else to populate it. And curated, or the gold layer, is actually where the analytics and the business insights are presented from, and that's the layer we use for machine learning for doing the learning, or possibly inference as well. But that's how that works. But essentially, it's getting you. Just think of it as a big cloud bucket, or lots of buckets with lots of exports of databases. There is messaging. We might come into messaging systems for live streaming, but it all comes into like big buckets, and then the applications are on top. Each cloud's got its own one. This is Microsoft's one. It's very same. One lake, again, just big cloud bucket. Data Factory is the tool that's used for converting stuff from one format to another. We've got the databases, we've got the data science, real-time analytics, powered by it's a platform for just writing simple apps that you don't need to do code. But Google, Amazon, Microsoft, and Databricks have all got their own stuff, but we'll explore open source equivalents later on in this video. So thank you very much. Hope that wasn't too long.